Okay, so we've seen in the previous video that um, the OS executes only when there is some format of an interrupt of an event, and there are essentially three ways these events can occur. So one is um, by interrupts, which could be either in the software, from the software, or interrupts that are triggered from the hardware. And the second form of event is due to exceptions, right, like a page fault exception, a divide by zero, and an illegal instruction. So software interrupts essentially are the system calls. In RISC-V, a system call is invoked from the user mode using the eCall instruction. Okay. Now we've already covered the process of software interrupts, how system calls are invoked, and we've essentially traced the execution of eCall from user mode to the supervisor mode in the address space of the process, then the switch into the address space of the kernel, execution of the system call, and then back to the user mode. So today we'll speak about hardware interrupts. So what exactly do we mean by this? So hardware interrupts are essentially events that get triggered from external devices, right? So if I essentially look at the CPU core, right, so this is my CPU core. Most CPU cores, we already seen multiple times that there is a reset input, but many CPU cores also have another input known as interrupt. So the CPU cores could have one or a finite number of such pins known as the interrupt pin, and this is essentially an input to the CPU core, and then you have an interrupt acknowledge pin. Right, so this is an interrupt acknowledge pin. So through this interrupt pin, right, an external device would be able to interrupt the execution of the CPU. In other words, external hardware interrupts would be essentially triggered by this interrupt pin. So what do I mean by this? So let's say we have a keyboard or another device connected to this interrupt pin, right? So any key pressed on this keyboard would essentially issue a signal which goes through the interrupt pin to the CPU core, and thereby interrupts the CPU core, and as we have seen, it would cause the switch typically from the user mode to the supervisor mode, and then in this particular example, the keyboard driver would execute and identify which key is pressed, right? So any external device like the keyboard or mouse or network or hard disk, things like that, if it wants to essentially request to be serviced by the OS, then it essentially sends the interrupt signal, right? But now we have a problem here, right? We've got multiple different devices which can possibly communicate with the CPU core, or which would want to essentially send interrupts to the CPU core, right? So keyboard, mouse, network, hard disk, and so on are examples of that. However, we typically have only one interrupt line in the CPU core. So how would one essentially handle multiple such devices which would want to interrupt the CPU core? So typically this is done with the help of a programmable interrupt controller. So we have a CPU core, and as we have discussed, we have one interrupt line to the CPU core. We have the reset as well, and what we do is connect this to a programmable interrupt controller or a PIC. So PIC stands for programmable Now, the PIC could have multiple lines at its input, right? Each line could be connected to a different device. For example, this could be connected to the keyboard, this to the mouse, this to, let's say, the UART, and so on, right? So what the PIC does, so the programmable interrupt controller does, is that it listens to it keeps track of all of these input lines, and then if it identifies that one of these devices wants to essentially raise an interrupt, it transmits that interrupt through the PIC into the CPU core, right? So for example, if there's a mouse click, then this click is converted and by the PIC and transferred to the as an interrupt to the CPU core. Similarly, an interrupt from the UART, for instance, if the UART has received a character or some data, so it would raise an interrupt, and the PIC would essentially transfer this interrupt to the CPU core, right? So we are able to multiplex this one interrupt line with multiple devices with the help of the PIC. Now, from here, everything works the same, right? So the interrupt would result in the switch to the machine mode or the supervisor mode, and the CPU would identify that this is due to an external interrupt through the interrupt line, and so this is done through the SCOS register, which we have looked at in the previous video. But the CPU does not know which device has essentially raised this interrupt, whether it was a keyboard, mouse, or UART. It only knows that an interrupt has occurred through the external line. So what the CPU core does is that it queries the PIC, the programmable interrupt controller, and essentially identifies which of these lines or which of these inputs have essentially raised the interrupt. Okay. So, so from here, the CPU core would identify that, say it was a mouse, the mouse that essentially raised the interrupt, and call the corresponding function to handle them, that would communicate with the mouse to identify which pin had essentially been clicked. Okay. So, yeah, taking it a bit further, now we move to a multi-core platform, right? So, in a multi-core platform, we now have multiple such CPU cores, say core 0, core 1 and core 2. Okay. Each of them would have their own interrupt lines. Right, and we would have a programmable interrupt controller as well. Okay. So here things get a bit more complicated, because the programmable interrupt controller, as before, would be connected to the interrupts of various devices like the keyboard, mouse, and UART, and so on. But it would also decide which where to essentially forward the interrupt, right? So, for instance, if the keyboard has essentially raised this interrupt, the PIC could be essentially configured to forward this particular keyboard interrupt to one of the different of the 3 CPU cores, right? So, this could be programmed into the PIC, or the PIC could use some kind of a arbitration algorithm or some kind of an algorithm to choose which of the 3 CPU cores in this example should the interrupt be forwarded to, right. So, things various things have been experimented with. For instance, there are systems where we have a dedicated CPU, for example the CPU core 0, which handles all interrupts, right. So, any interrupt that occurs would essentially be handled by CPU core 0, while the other cores essentially are used for computation purposes. Another scheme could be that the PIC kinds of uniformly schedules the interrupts across the various CPU cores. A third scheme could be that the PIC kind of detects the workload on each CPU core and identifies the CPU core which is least loaded and forwards the interrupt to that particular CPU core. Okay. So, now what we have in such a platform is that every interrupt that occurs would have to go to this PIC, which is shared among multiple CPU cores, and then the interrupt would essentially get forwarded to one of these CPU cores, right. Now, the good point over here is that this PIC could kind of balance or can be programmed to have a flexible way how interrupts can be transferred to one of the multiple CPU cores. However, there are some interrupts which uh, are needed specifically for each CPU core, right. One such example is the timer, right. Now, if you are running an OS on the CPU, then you would require a timer, specifically if the scheduling algorithm you use is supports multitasking, right. So, as we have discussed earlier, the timer would essentially decrement until or change until it reaches a particular value, and then it raises an interrupt. This interrupt would be forwarded to the corresponding CPU core and would trigger the scheduler to execute and cause another process to move from the waiting state to the running state, right, or move from the runnable queue into the running state. Okay. So, typically what is done is that each CPU core would require its own timer. So, for example, we have timer 0, timer 1 and timer 2. Right. So, one way is that each of these timers are connected to the PIC. Timer 0, the interrupts from timer 0 are targeted to core 0, the interrupts from timer 1 are targeted to core 1, and that of timer 2 are targeted to core 2, right. So, each of these cores would run independently, would independently service the timer interrupts, run the scheduler and choose a particular process to execute independently. But the problem with this model is we have timer interrupts occurring periodically and using the shared PIC, right. So, this would create overheads, especially because this PIC is essentially shared among the various CPU cores. So, multiple scenarios in this particular case use two different programmable interrupt controllers. One is the global PIC or the global programmable interrupt controller, and the other one is a local controller. Okay. So, the typical architecture for such multi-core processors, including RISC-V, would look something like this. So, we have the multi-core processor. and associated with each processor we have what we call as a local interrupt controller, right. And we also have the global interrupt controller as well. So, local interrupt controller is connected specifically to each core, and the global interrupt controller, as before, is shared among the various cores. Okay. So, interrupts which are dedicated to a specific core, such as the timer, would be essentially connected to the local interrupt controller, while other devices like keyboard, mouse and so on, the interrupts from them are essentially routed to the global interrupt controller. So, this way we like critical interrupts such as the timers do not share the common global interrupt controller, right. The nomenclature for RISC-V based multi-core platforms is slightly different, but the in at a high level this is what essentially happens, right. So, in RISC-V with multiple cores, the cores are called Heart0, Heart1 and Heart2 as we have seen before. We have a local interrupt controller which is in this case shared for the 3 CPU cores, and we have a platform level interrupt controller called PLIC, which is essentially the global interrupt controller, which is connected to all the 3 CPU cores, in this case the Heart0, Heart1 and Heart2. So, the local interrupt controller generates different timer interrupts independently for each heart, right. So, you have a timer interrupt which is created from the CLINT, the local interrupt controller, to Heart0, another one for Heart1 and a third for Heart2, right. While devices like the keyboard, mouse and so on are connected to the platform interrupt controller, and the PLIC essentially would route these interrupts to one of the 3 hearts based on some scheduling algorithm, right. So, let us say we have a device here which has raised an interrupt. This gets routed by the PLIC to, let us say, Heart1, right. And now Heart1 goes into the interrupt service routine and queries the PLIC to identify the cause for the interrupt, right, whether it was from the keyboard, mouse and so on. It would then identify the cause for the interrupt and invoke the corresponding service routine. Okay. So, we will start now with the PLIC, and we will essentially trace the XP6 code to see how the platform level interrupt controller essentially works. So, a quick recollection. So, whenever an interrupt occurs, whether it is a software interrupt, exception or a hardware external interrupt, so the hardware stores the program counter in this register called the EPC, the exception program counter. Then, depending on whether it is in the user mode or the kernel mode, would essentially invoke the user vec or the kernel vec, right. But before doing so, it would essentially switch to the supervisor mode, right. So, for instance, if one was essentially executing a user program in user mode and an event occurred, the program counter is stored in the EPC, and the hardware automatically switches from the user mode to the supervisor mode, uses the STVec register to identify where in the supervisor mode it should execute, and in this particular case it happens to be the function user vec. Uservec essentially stores the various registers, the stack pointer and so on in the trap frame, and invokes this function called user trap, right. Now within user trap.c, within user trap present in trap.c, the cause for the interrupt is essentially identified, whether it was a hardware interrupt, whether it's a timer, it's a system call, or an exception. Now if the cause, so the way this is essentially identified is by using by looking at the scos register, right. So specifically this is the scos register, and if the most significant bit is set to 1, it essentially means that an interrupt has occurred, okay. And and further, the interrupt is an external interrupt or a supervisor timer interrupt, then the corresponding exception code would be either 5 or 9 respectively. Okay, so using the using the scos register, user trap identifies the whether it was a external interrupt, a timer interrupt, and so on, right. It then invokes this particular function called device interrupt. So the job of the device interrupt is to look into the platform level interrupt controller and identify which of the many devices that are connected to the PLIC have essentially raised the interrupt, right. So whether it is the keyboard, mouse, UART, and so on. Okay, so the device interrupt function looks something like this, right. It invokes the, first of all, invokes the scos register, and it notice that it is checking the most significant bit over here, which corresponds to this bit. This is a single bit, and this essentially set to 1 if it is due to an interrupt, a timer interrupt, or an external interrupt. So this is what is set over here, right. If it is due to this this interrupt, it enters into the if statement, and here we have a check to identify if the scos, the lower 8 bits is equal to 9, right. Recollect that 9 essentially means that we have a supervisor external interrupt. The interrupt is essentially coming from through the PLIC, the platform level interrupt controller, right. So what we then do, right, so the next job for the OS is to identify which of the many devices, the hard disk, the UART, and keyboard, and so on, has essentially raised the interrupt. And the only way to do this is to communicate with the PLIC. Now this is essentially done with this function called PLIC_claim, the details of which are very specific to the PLIC that is used. But what is actually important for us is the return from the PLIC, which is essentially IRQ. So IRQ essentially would tell us which of the devices has essentially raised the interrupt. So for instance, if IRQ is equal to UART 0 IRQ, then it is the UART interrupt which is raised. If IRQ is vert IO 0 IRQ, then the interrupt is essentially raised from the virtual IO disk, that is the secondary storage device, right. So UART interrupt and vert IO disk interrupt are essentially the device drivers. They are the handlers for these very specific devices, right. So just as an example, we will look at the UART interrupt, right. So what happens when there is an interrupt from the UART? So recollect that for the XP6, we use the UART to essentially communicate with the user. So the keyboard and the peripheral and so on, any data sent into the XP6 is sent through the UART. Similarly, anything which gets printed out is also printed through the UART. Okay, so if I press a character on my keyboard while XP6 is running, this goes through the UART. It results and through the UART present in the emulator, which is QMove, and QMove would raise an interrupt. This would be the UART interrupt, resulting in this function called UART IR interrupt to execute. So, the function is present here, which is essentially here. So, we see that this function UART interrupt would execute, and what it does is it reads the UART to get the character that was essentially typed in, right. So, what was essentially pressed on the keyboard, and this character, which is stored in C, is then essentially displayed on the console, on the terminal, through this console interrupt function, right. So, you can go through this console interrupt function to identify how the interrupt essentially is displayed on the screen.